An honor to be here. I thought I'd put together a few thoughts to get the juices flowing for the next day and a half. In particular, thinking about framing the questions about safety by thinking about the fact that the methods that we call AI, it's a constellation of methods actually, will likely be touching our lives more closely and intimately than many other computing technologies and other machinery. And we see in the last, I'd say 10, 15 years, AI steadily moving into healthcare, transportation, finance, public policy, defense, among other areas I would call high-stakes applications. And as this is happening, we see much to do on principles, methods, and best practices. Think about the large universe of computer science. So many areas under development over the last several decades have deep relevance to the safety questions, building safer AI systems. This includes the work in probabilistic AI, planning, machine learning, sensor fusion, older but continuing work in control theory, ideas about meta-reasoning and thinking, reflecting about the operation of machinery, multi-agent systems, design of mechanisms that have certain provable properties, for example. Older areas from management science, robust optimization, for example, and operations research are quite relevant. And we heard earlier security verification and cryptography are deeply promising. We'll see certain challenge problems. And of course, we can't forget HCI. These machines work with people typically, and there's quite a bit to do in the space of innovation around human-computer interaction. I wanted to also make sure that we understand that there's a whole field called safety critical systems that spans or crosses through multiple engineering disciplines. And it's kind of interesting to think back about sort of what safety critical means, and bringing up definitions today might be useful. So safety critical is defined as systems whose failure could result in loss of life, significant property damage, or damage to the environment, designed or needing to be fail-safe for safety purposes. Fail-safe. I thought coming to Pittsburgh would be very interesting today to think about fail-safe for a variety of reasons. Fail-safe devices are work in the event of a failure to respond in a way that will cause no harm, or at least minimize harm, or a fail-safe device incorporates some feature for automatically counteracting the effect of an anticipated possible source of failure in advance. Why did I say Pittsburgh? Well, we're actually our ground zero for fail-safe technologies, it turns out. And the George Westinghouse, at the 20-year-old, in this area in Pittsburgh, saw a big train wreck and dug into why did that happen. And he came up with this, the core canonical example of fail-safe technologies, coming up with this idea of using compressed air for a braking system where the brakes are actually held off in the off position by a working complex system. And if any piece of that system fails, the brakes snap back naturally to the on braking position. This fail-safe design air brakes about 147 years ago to the day was tested when George was just 22 years old, and a train left from Union Station here in Pittsburgh to Steubenville. Now, since then, quite a bit's been going on in the fail-safe arena. So there are some standard practices, for example, fail-safe processes and practices. When fighter jets land on aircraft carriers, the standard is, as they go with what's called an arrested landing, is to turn on full speed, full throttle with afterburners in case they're needed, in case there's a failure and the jet has to take off again. During the Apollo era, physicists and engineers generated free return trajectories. If anything failed, the Apollo module would come back to Earth on its own, a plan. So we see mechanism, practice, and plan. And people that are familiar with air brakes know that there's something called a wig-wag, wigs and wags. And it gives you a sense for the actual status of a system. So there's a monitoring component as well. How is my system doing? Which is very, very important to think about as we get our juices flowing about safe AI systems. Now, what makes AI special? We heard a little bit about this from Bill earlier, and there are a number of special considerations. The big one for me, and I think for all of us, is open world complexity, which leads to incomplete understandings. There are uncertainties and poor characterizations of performance of our systems There are poor operating regimes, and unfamiliarity of the form, we can't even characterize the performance. There's a rich ontology of failures. We're not talking about a break failure. We're talking about very different, diverse modalities and new attack surfaces. Who would imagine that we're now thinking about machine learning attacks by adversaries that can inject new kinds of data beneath the radar into our classifiers, or self-modification systems that are very, very bright that can actually start to modify their own reward function and change their behavior, shortcutting the intentions and goals of the designers. And numbers of unmodeled influences. We design a system to do X and Y, but A, B, and C happen, and they're costly. They can be costly. Another challenge is transferring our solutions across space and time. We can't just build one air brake and move it around because we have distributional changes, evidential changes. Our models age out over time as well. They don't stay fresh. The really interesting challenge of coordinating human-machine collaborations can lead to severe costs, and I'll get to back to that in a few minutes. And then this idea of operational opacity. Unlike an air brake and many systems that are built in more traditional fields of engineering, we have intrinsic challenges of opacity in our systems today. And there's great work going on in making our systems more transparent. Now, we heard about the frame problem earlier. When I was in graduate school, the frame problem was kind of an interesting theoretical question. How could you tractably understand in a bounded system all the consequences of an action? The qualification problem is how do you understand all the preconditions required for the actions to have the intended effects? And then the ramification problem on the other side of things, how do you understand all the important downstream implications of an action in the world? And it was really just a theoretical question, and we talked about it, and you can do some interesting logic about this question in a theorem-proving system. But with the rise of AI and moving into the real world, we really had to grapple with practical versions of this problem and understandings of it. In a really, I'd say, success, we've seen the rise of probabilistic methods. These are the known unknowns. How do we characterize uncertainties and then propagate them and use them and make decisions under uncertainty? I'll give that a gold star, a red star. We made great progress there. I think we're doing quite well there. That doesn't mean it's a solved problem. And we're seeing more attention now to the unknown unknowns, where our model is incomplete in ways we don't even understand yet. We can invest more effort into making them bigger and more comprehensive, but we don't understand or even to recognize when the system is operating in an unknown situation. Let me give you a couple examples here. Here's my daily commute. I see a Tesla display on my way to work, and once in a while, there's a known unknown. The system understands that, hey, I can't do well now. Please take over. And it tells you very quickly to grab the wheel, no matter what you were doing. But a few weeks ago, I was driving along late at night on 405 South. I said, well, looked up. The car's in autopilot mode, zooming along at 70 miles an hour. So what's going on down there? It's kind of weird. The system had no ability to recognize or understand what to do about this anomalous, non-engineered, unknown. I was curious. Should I let the car just do its thing? I decided, no, it's going to hit him head on. It's going to hit him without any knowledge. So we have decision-making under uncertainty, but known unknowns, and then incompleteness as well. Think about the challenge problem of building a Tesla, for example, or any kind of automated car for driving. Engineers will sit and look at different situations. They'll consider issues like challenge problems, like we'll call them safety critical problems, like bicyclists, understanding. But then you have these situations that just weren't weren't in the conception of the designer's mind. A bicycle coming around a bush, for example. Quick person skidding through the street, a little kid, or a ball snapping onto the windshield with probably a person following it. So what do we do about these issues? And I'll talk about some directions here. First, on known unknowns, there's been a really nice a body of work on learning about the abilities and failures of systems. We go on a database of successes and failures. We want to build a predictive model of confidence given some observations. And with the interest in deep learning these days, we now have deep learning about deep learning performance. So people are actually applying multi-layered systems to understand for example, can I predict how good that caption was after it comes out of a deep learning pipeline that automatically captions? Some earlier work I did with Kitara Toyama, we said, okay, let's look at pose tracking. We said, okay, we have ground truth, and it leads to some inferred state of the system. But there's some idea of reliability of the inference, and we can generate these observations, reliability indicators. And they can be used to tell us how likely, how truthful that state is. And it turns out you can make portfolios. So by having individual, very different kinds of pose trackers and face tracking systems, almost independent, you can do the same kind of modality investigation and modality reliability investigation on all three systems, and then together build a model that knows how to weight, a unified model that weights together the three models and their reliabilities to give a very much more robust portfolio solution. And so one idea to robustness is via generating analytical portfolios of multiple independent, maybe overlapping a bit, but independent methods that are each looking at a problem differently and characterizing the uncertainty and reliability of each, which can be context dependent. There's a whole area of robust optimization. So even if you didn't know all the knowns and unknowns, you might say, okay, let's make our problem more robust and resilient in general, give it robustness. So there's an area of robust optimization where the idea is to optimize under uncertain parameters. And one approach to this is a kind of a trade. You say, well, my current default system has this kind of payout over here with some possible severe costs, but a very big upside. You say, I'm going to give up some of the upside here, push back on the upside, because I want to basically restrict the downside here. So you can actually, under uncertain variables, say, I'm going to give up on the upside and have a more robust solution that has a lower expected payout. And more generally, in the medical decision-making community, I think we need to do more of this in AI, is sensitivity analysis. So it's wiggling our various variables from their midpoints. Like, let's say we have a set of probabilities. We assume they're kind of midpoints. But what if I just, and using my analysis, if I wiggle each one quite a bit, let's look at how the decision policy might change. So you see here are three regions as a function of two parameters, a probability of a stroke in healthcare and a probability of complications during a revascularization surgery. And you can compute expected as a function of these two parameters, what's the best decision in different cases. And the idea basically is to say, well, I'm going to wiggle the probabilities in my system and see how deeply inside a decision region is my current best guess. And if you're embedded deeply, you can say that the probability you change the decision given unknown unknowns is lower. And there are many different kinds of these robustness analyses in healthcare. I've seen very few in AI research. And then there's an interesting direction in learning about unknown unknowns. Sounds like almost like something that would be almost impossible, but as you imagine, as you expand the model with experience or data or doing rich simulations, if you have a nice simulation model, you can generate new distinctions and learn more about regions of the space that your initial solution did not cover. You also can just generate methods that can detect anomalies like strange colors. Imagine my Tesla, all of a sudden, if you see strange orange or white or blue in front of the car, it's probably something that I don't know about. It might be an anomaly. Let me ask the human being to take the steering wheel and take over and give up. There are various ways to detect anomalies and distributional shifts from evidential patterns more generally across domains. And then the idea of doing meta-analysis and transfer, understanding how models get better with effort of various types and data in different domains, and saying I can assume that again in a new domain. There's an interesting issue on human engagement. People often know about many unknown unknowns that a system does not know about. When I was driving a Tesla, I immediately knew what the situation was by just looking up. Thank God I looked up in time instead of talking to my hockey team buddy who I was talking to during the ride. I looked up, I said, hang on, give me a second here, this is interesting. As a human being, I knew more than the car did. So there's been some interesting work, in particular Attenberg, Periotis, and Provost did some work on a system called Beat the Machine. And this is an interesting example of how you can engage people in advance of fielding a technology, where classifiers were built to look for hate content on the web. And here's the classifier, and here's how well it's doing. You see at the midpoint of this line here, trying its best to divide up non-hate from hate. There's some uncertainty in this region here. And the system has a confidence score based on how uncertain it is, how close to that region in general a point might be in that space. Well, in Beat the Machine, people played against the classifier that was built to date, and they got paid or rewarded for beating the machine. And they identified disjunctive areas that were hate that the system had no idea about, because hate's a pretty interesting topic and it's pretty heterogeneous, and won points by finding these regions. And the idea is to engage people to help with fleshing out a system, changing unknown unknowns in a system. Here's another example of probing the unknown space. Some work I did with John Crum several years back. We had a system that can predict where users are driving as they drive. And it turns out knowing locations that they've been to before and they stopped at, known destinations, is really important in doing a precise job. If you don't know where they're going, you apply an open world method, which is quite different and much weaker. Well, the question is, could we learn from data across hundreds of people to predict, given the prior destinations and the dynamics of how someone's driving in real time, whether or not they're heading to a previously unknown destination or a new destination over time? And you can look at one of the key variables is how long have I been watching this person in the database here. So one of the variables here is observed days in the database for this individual, and we're going to compute dynamically closed world or open world. Do I know about this, or is it an unknown, and fold that information in to build a better algorithm. Now I'll talk to you about some platform ideas. So there's the idea of taking the best of breed. There's a little drone flying around here. And to do joint modeling of multiple dimensions of error at once. So I'm referring to some work here right now where we try to learn the errors of perception with limited sensors on the drone, as well as errors of control, the ability to control a system. And this is work by Dorsa Sadig and Ashish Kapoor. Dorsa is with us today here from UC Berkeley. She was an intern with us last summer. But the basic idea here is that you can sort of learn from data, and depending on how much data you have, you get tighter or weaker bounds on a distribution of what the system will do in different settings, and have probabilistic models of the ability to control, like a roll, and probabilistic models of the ability to see an obstacle. And the basic idea is, if you build this system with machine learning, feeding, control, theoretic, you can build a system that how to uncertainty, and it can run a simulator in real time for any proposed trajectory it comes up with, and compute, given both those uncertainties, what's the likelihood it's going to basically be safe. Now in this case, we're defining safety as probability of no hitting a wall greater than 1 minus some specified epsilon. And we can compute that in real time by understanding, for any trajectory, how many times did that go over that bound. That gives us a model of safety, formal safety. So what happens is in real time, the system is generating trajectories. It's finding one that's that's greater than 1 minus epsilon in safety, and then it uses that policy in a piecewise linear way to navigate in a room with an objective function. It gives you an idea when you run this platform, you can run a simulator or the real thing. The red is the inferred ceiling. As the system moves on with very weak sensors, but they're characterized in a way. And once you have this model, then you can say, given how well this works, what's the value of refining the system with more data, with better sensors, a better controller, and characterize the cost-benefit to getting better paths that might give you a 1 minus epsilon even smaller, for example. Now, you can apply this in Failsafe, back to George, in a way that would make George Westinghouse happy here. The system basically, in this case, was being used in an outdoor drone here, and it could, as it was moving along, it could not find a path that would satisfy probability of safety greater than 1 minus epsilon, and it went into a fail-safe mode, which is stop and go up and hover, designed into the system. The same methods with sensors and probability of control can be used with a probabilistic language to actually design how cars might work someday with a 1 minus epsilon again, formal model of safety. Changing topics, I want to just point out that I think there's I think it's a very fertile area to think deeply about, and Bill referred to this earlier, is the link between cybersecurity, cryptography, and verification, how innovations here will support safe AI systems work in the future. There are many different areas of security and verification that I think that have lots of implications for safe AI. Static analysis. Can we prove the system will do the right thing where right is defined in some clear way? Of course, that's a challenge problem in itself. If we can't verify a complicated AI system, can we do runtime verification? The idea now is thinking that I at least know what properties I want to avoid. Can I have a monitor that can actually do runtime verification? White box fuzzing is a fabulous technique. We're using an AI theorem prover to help flesh out and test all the paths that might be relevant in a system. And other areas as well, some are quite hot topics in cybersecurity right now. For example, the idea of mixes of software and physical security to protect both data integrity and inter-process communications. So again, runtime verification is a whole community doing this kind of work now in the verification, the RV community. They say, well, listen, I can't, without errors, or even attempt to do a formal analysis of a large-scale AI system. We want to basically now analyze and execute information that might be emitted by an AI system as events, and maybe just ask ourselves, do those events satisfy or violate a desired property? And they can be used to identify a problem, to engage a person, or again, say, if I see this in my RV, my verified runtime verification component, take a fail-safe action if I see X, Y, or Z occur in the base level system. Now, we'll be hearing a little bit later from Amadai and work with him and Chris Ola and others, and Bill this earlier. Think about more general AI systems that learn, for example, reinforcement learning in the environment. Here's the environment, which emits a state that's observed. AI system takes an action, changes the environment, new states observed, a reward is given, and there's a kind of a learning system that gets better and better over time. These are more general open world reasoning systems, and they come with their own interesting challenges, several of which Dario and Chris and others talk about in their paper. It's been a concern for many people for quite a while in terms of how we grapple with various aspects of these systems. For example, the systems have some way of taking state and assigning reward, a function to assign reward as a reinforcement signal. They also understand how to perceive. They can perceive states in the world. And you can imagine if those surfaces were exposed to an adversary, how that could be, a smart adversary can manipulate an RL system. And not just a smart adversary, but let's say we have a very, very smart computer program. And it itself can sort of take a look at how it sees things and how it reinforces itself, and decides to shortcut its reinforcement the way a drug addict would reinforce it might reinforce him or herself, and not act in accordance with the wishes of the human designers. Now, my comment on this is that there's a whole bunch of opportunity for reflective analyses, and I basically say, using runtime verification and static analysis, that would understand what the sensitivities might be, the ones that we know about, and ensure operational faithfulness, or ensure isolation of modules, or identify that external meddling from the meta level. I'm hopeful about that in general. I wanted to now a little bit about, to keep the juices flowing, human-computer interaction. You might not call a autopilot an AI system, but other people might say, no, at least from the point of view of, let's say, George Westinghouse, that's a really smart system, and it's a system of the kind that's working with people. We're going to see more intensive symbioses and engagements in the future. Consider the case of China Airlines 6 in February 1985. I remember when this happened. I was in graduate school. A 747 heading from Taipei to Los Angeles had an engine failure on one of its wings. It was in autopilot at the time when the failure occurred. And the autopilot did its best to keep the system up in stable flight, but it was processing a bit, per my understanding of the story. It was a complicated solution from the point of view of the autopilot. At some point in time, I imagine the pilot yawning and stretching and turning off the autopilot, not exactly knowing the solution the autopilot had come up with. And the lack of awareness and the difference between what the pilots thought, these were very experienced pilots, by the way, and the plane was doing, led to the plane to dive about 10,000 feet in 20 seconds. It's the only recorded history of a 747 going supersonic and having its wings bent, and the passengers experienced 5 Gs. Luckily, it righted itself right a few thousand feet off the water and landed with bent wings at SFO. And I hear the plane is back in flight again today, so if you're flying on China Airlines, maybe you should check the body of your fuselage. The other more sadder situation was Air France 447, June 2009. It's probably more fresher in our memories, where because of an awareness problem, when the autopilot and the Airbus shut down with not sensing airspeeds because determined to be a pitot tube freezing problem, went into an unrecoverable stall as the pilots did the absolute wrong thing, keep the plane in stable flight. So if you think about it, our systems today, and I don't think I know my test, one of these systems, doesn't have a model of human cognition. There's no really transparent state or explanation for what's going on, for what the solution of the system is. And there's an opportunity to master the coordination of initiatives from humans and machines in the future. Think about it, there's a kind of a spectrum of autonomy. I don't want to get too Tesla-centric in my talk today, but there it is again. Each of these solutions involves human cognition and machine intelligence in some way, and we can certainly learn about the best ways to, from the point of view of an automation process or an alerting process or a coordination process, the best way to use both and to alert, for example, humans to help when the machine can't do a good job in a safety-critical setting. There's a whole design space in an engineering sense for a mix of initiatives here as well. So in thinking about this problem a bit, one more Tesla story. When I got the Tesla, I think Doris has been in my car. We've taken people out for test drives as field trips in my car, and we try different things out, and then we come back to the office and we think about, well, how can we make the system better? It has to be better someday because I think it's very dangerous right now. It's just a matter of time before we see some high-profile stories about its failure, even if it's doing a great job to enhance safety overall. And so one idea is that we actually know where people grab control. I've spoken to the head of the vision team at Tesla, and they have a big database. So with millions of miles monitored so far, where people take control, so we actually understand where there are challenges with competency the system has, and we can sort of observe or infer those. And then the basic idea is, if a car is moving into one of these regions, can we monitor attention of a user, for example, over time? And we've done that in the past for other systems, other applications. We also have done work on where is the user going right now over time, and automatically have systems that do safety assurance coordination by understanding the need and status of a driver's attention over time, the latency of what it would take to get human input, the latency tolerance of a situation. What if I can't get the person to respond within 5 seconds right now? The cost and influence of alerting a driver if they didn't really need the driver. Maybe it's a false positive. And the idea of a custom language, ongoing dialogue, where it might be a tonal system, for example, where a system can try to get the driver's attention to be more aware. If they can't, maybe slow the car down to defer the need. And if you can't, and it's a challenge, go to Failsafe, which might be pull over with flashing hazard lights in a special lane, made just for automatic cars, for example. All right, let me just end by saying that I'd like to be thinking about, and tomorrow's group, and our governments, and our private sector people, what are some best practices for safe AI? I think we start asking this question. Of course, for many of these, the devil will be in the details. But for example, with drug and medication work, there are classical, understood clinical trials and phases of clinical studies that are required for safety. And then there's a post-marketing vigilance phase as well that continues on. So shouldn't there be phases of study, and I don't mean for activity in the government necessarily, but just as best practice for now, phases of study for testing and reporting when you roll out new capabilities into the open world in safety critical domains. Another best practice might be disclosing parameters on failure rates, trade-offs, and preferences of a system. So I don't really understand right now, besides playing with my car, which I view as a kind of complicated horse, what's going on in terms of the failure rates and how well it does. It tells me once in a while, take the wheel, but I don't really understand the trade-offs there and preferences. We want to have best practices for transparency and explainability of perception, inference, and action. These are, by the way, it's a very challenging area. There might, on the engineering front, we might need some best practices with self-monitoring and reporting machinery in our systems. Imagine something with a standard. If you have a reinforcement learning system, everybody expects there to be monitoring of the reward function and its dynamics over time. We might also want to impose, as best practice, isolation of different components in an architecture. This component cannot absolutely, per verification, cannot modify that component. And here's why that shouldn't happen. In systems that I've already fielded myself and my teams have fielded, I know we can do a better job at this. How do we detect and address feedback of the system's own influence in the world on its performance? A readmissions manager, for example, that decides which patient should get a special program to keep them out of the hospital for more than 30 days, and it does special things. Well, that might be distorting the population. And does the system know how to handle that and reason about those new patients that got interventions directed by the model itself? People want to read some work I did with Ryan White. Turns out that some results coming up on the web, when you put in some basic symptoms, are coming to that are about rare, scary diseases, are coming to the top of the search list because anxious human beings click on those all the time. And guess what happens when the rare diseases is at the top of the list when you have a little twitch in your thumb? You believe that that's a likelihood. And you have a feedback problem with search results, which is a machine learned, both Bing and Google, my understanding, machine learning system. Just a few more best practices. You probably heard from my last couple of slides before about human-computer interaction that I'm passionate about the need to develop, just like a brake and accelerator and a steering wheel in a car, no matter what you're doing, potentially generalizable, what are standard protocols for handing off control between a machine and a human being per attention, awareness, warning, and alerting in human-machine collaborations? Another issue is what are sets of fail-safe actions and procedures given predicted or sensed failures in different domains? Then there's a big opportunity we often think about systems in the abstract. We're going to build a great system that's going to be in the open world, but there's such an incredible set of best practices for co-designing, possible, I should say, co-designing the environment with our systems. Maybe little beacons or special paint on highways will make automatic cars much, much safer. why don't we think bigger, think about the whole ecosystem for best practices? Again, best practices for drift assumptions and distributions of domains. In a medical system that we built, the actual definition of lab results over 2 years of data changed. Oh, no. We're using a different machine now. This one's from Cerner. You mean the evidence isn't the same anymore? Yeah, we call it the same thing in the model, but that you learned last year, but we haven't really figured out how to adapt the new evidence to the old model. The drift happens all over the place in machine learning and decision making. And then the basic idea is, there was a ProPublica piece that came out a few weeks ago, which brings this to mind. I think that we need to have special practices, special best practices to have openness and adherence to certain kinds of policies when we have data, learning, and decision making for applications in governance and public policy. Those data sets should be open or should be accessible for scholarly probing and activity, so we can sort of bang against them and see, are these biased? Or are they, what do we think about them, and so on. We don't understand when it comes to governance and public policy, for example, systems that we're using to categorize people by the probability they'll come back to a court appointment, or that they won't commit a crime while they're out on bail. I view this as core safety for our civilization. And I wanted to end, because there's this elephant in the room, and several people in this room are here because of this. There have been ongoing concerns about superintelligence. I want to just raise this concern. And I believe that it's very, very important for scientists to address the concerns of the public and of experts about this topic. I have to basically relate to this group that it's not only the public, but numerous computer scientists have told me, of quiet settings, that they themselves are concerned about very bright intelligence. So there's a significant difference of opinion, and of course we have a lot in the press right now. There's been interesting over the years, Jay Good and others, about intelligence explosions. I want to just end by putting up one document that I found in a museum in Montana. This was a transcript that Alan Turing read on the BBC in 1951. This is Alan Turing's handwriting here, where he's pointing out that it seems possible that once the machine thinking method had started, it would not take long to outstrip our feeble powers. They would be able to converse with each other, to sharpen their wits. At some stage, therefore, we should have to expect the machines to take control in the way that is mentioned in Samuel Butler's Erewhon, or Nowhere Spelled Backwards, which was a 19th century novel about really smart and bright machines taking charge. So my point there is we have to continue to ask ourselves not just all the questions that might seem more reasonable about security. Do we understand possibilities of loss of control of various kinds, even temporary? What kind of research could be done in this space? Is it beyond our ability to research? Is it too early and premature? Can we backcast from imagined poor outcomes and come back and say, how could that possibly happen? And we can design ways that would put everybody at ease, including the public, that we can thwart possibilities and ease concerns in this realm. So I'll stop there.